Welcome to Introduction to Structural Analysis for Beginners. I'm your instructor, Engineer Patrick, and in this course, we will explore the fascinating world of structural analysis. This course is designed for beginners who are interested in understanding how structures behave under different loading conditions. So, let's dive right in. In our first lesson, we will discuss the importance of structural analysis in the field of civil engineering. Structural analysis allows us to understand how structures, such as buildings, bridges, and towers, respond to various forces and loads. Here are some key reasons why structural analysis is important. 1. Safety. Structural analysis helps identify potential weaknesses, vulnerabilities, and failure modes in structures. By analyzing the forces, stresses, and deformations acting on a structure, engineers can ensure that it is capable of withstanding expected loads and environmental conditions, minimizing the risk of collapse or failure. Two. Design optimization. Structural analysis allows engineers to assess different design options and select the most efficient and cost-effective solutions. By analyzing the structural behavior, they can determine the appropriate size, shape, material, and configuration of the elements, resulting in optimized designs that meet performance requirements while minimizing material usage and construction costs. 3. Performance evaluation. Structural analysis enables the evaluation of a structure's performance under various load scenarios, including static, dynamic, and environmental loads such as wind, earthquakes, or temperature changes. It helps engineers understand how the structure will respond to these loads, assess its deflections, stresses, and deformations, and ensure that it meets performance criteria and code requirements. 4. Structural integrity. Structural analysis aids in assessing the integrity and longevity of existing structures. By performing inspections and analyzing the structural behavior, engineers can identify any signs of deterioration, damage, or excessive deformation. This information allows them to make informed decisions regarding maintenance, repairs, or retrofits to ensure the continued safety and functionality of the structure. 5. Innovation and advancements. Structural analysis plays a vital role in enabling innovation and advancements in engineering. By understanding how structures behave and interact with their environment, engineers can develop new materials, construction techniques, and design approaches. This knowledge helps push the boundaries of structural engineering and allows for the development of more sustainable, resilient, and efficient structures. Now, let's delve into the fundamentals of structural analysis. We'll start by understanding basic terms and concepts that form the foundation of this field. 1. Structure. A structure refers to a system or arrangement of elements designed to support loads and provide stability. It can include various components such as beams, columns, slabs, walls, and foundations. 2. Load. A load is a force or combination of forces applied to a structure. Loads can be classified as dead loads, permanent loads like the weight of the structure itself, live loads, temporary loads like occupants or furniture, and environmental loads, wind, snow, earthquakes, etc. 3. Support. A support is a point or region where a structure is constrained from moving. It can be a fixed support, fully restrained against translation and rotation. A roller support allows translation but restricts rotation, or a hinge support allows rotation but restricts translation. 4. Stress. Stress is the internal resistance developed within a material in response to external loads. It is typically expressed in units of force per unit area, such as pounds per square inch, psi, or pascals pa. Stress is a measure of the intensity of the forces acting within a structure's components. 5. Strain. Strain is the deformation or change in shape that occurs in a structure under the influence of stress. It is a measure of the relative displacement or elongation of the structure's components and is usually expressed as a percentage or a decimal. 6. Elasticity. Elasticity is the property of a material that allows it to regain its original shape and size after the removal of loads. In structural analysis, most materials are assumed to behave elastically under normal loading conditions. 7. Deformation. Deformation refers to the change in shape or size of a structure under the influence of loads. It can manifest as axial deformation, change in length, bending deformation, curvature, or shear deformation, displacement of layers. 8. Equilibrium. Equilibrium is a state in which a structure is in balance, with all forces and moments acting on it being equal and opposite. In structural analysis, the equilibrium equations are used to solve for unknown forces and reactions within the structure. 9. Structural analysis methods. There are various methods for performing structural analysis, including analytical methods, such as the method of joints, method of sections, and moment distribution method, and numerical methods, such as finite element analysis. 10. Safety factors. Safety factors are applied to the loads and strengths of a structure to account for uncertainties and ensure a margin of safety. They are used to prevent structural failure and account for variations in material properties, construction quality, and loading conditions. These are just a few fundamental terms and concepts in structural analysis. The field is vast and involves many more advanced concepts, techniques, and methodologies, but understanding these basics is a good starting point for exploring structural analysis further.